I will introduce our next speaker, another dear friend of ChainSafe's, co-founder of Celo, Marek Olszewski. Marek, why don't you join me on stage and share your screen? And how you doing, Marek?
Hello, it's really great to be here. Thanks for having me.
Absolutely. With that being said, the stage is all yours.
Amazing. Let me just share my presentation. Cool. Well, it's really great to be here. Hello, everyone. For those of you who don't know me, my name is Marek Olszewski. And today we're going to be talking about what's next with Plumo. Plumo is Celo's Featherlight SNARK-based syncing mode. And yeah, let's begin. Oh, and I also love the beard that Greg was sporting. This is the best that I can pull in terms of my quarantine look. I've been growing my hair out, desperately in need of a haircut, as you can see. So let's begin. So for those of you who are new to Celo, Celo is a new scalable proof-of-stake based permissionless platform. It's fully EVM compatible, and it makes financial tools accessible to anybody with a mobile phone. It launched earlier this year in April for Earth Day, and its mobile focus, I would say, is really what makes it kind of unique. And on that platform, C Labs, which is the company that I work for, launched Valora, which is kind of our flagship social wallet built on top of Celo, and it's now available for on Android and for iOS. It's now seeing growing usage in the Philippines, in Kenya, and also in Brazil. And you can learn more about it by going to valoraapp.com. And if you forget that there are 2 A's in Valora app, that's okay, we'll redirect you. And so Valora looks a little bit like this. It is modeled heavily off of centralized social wallets and really focuses on the payments use cases, kind of rather than the more traditional store of value use cases that you're seeing kind of in today's wallets. And we've been able to implement this and have it have kind of this experience that, again, kind of rivals centralized offerings. Really because of kind of 3 big kind of technology innovations on the Celo platform. The first is that Celo has a built-in kind of stablecoin platform, which allows you to create multiple stablecoins that are all pegged to different fiat, that are all over-collateralized and backed by the same kind of crypto asset over-collateralized reserve. These tokens are implemented as, or these stablecoins, I should say, are implemented as ERC20-like tokens on the platform. But critically on Celo, you can pay for gas using tokens. And so it's really easy to send and receive these things. Next, you may have seen kind of on this screenshot, you see a bunch of names and photos, really kind of underscoring the kind of the social nature of the wallet. This is really enabled through kind of this built-in lightweight identity protocol that maps hashes of phone numbers to public keys. So this means that you can find each other by phone number, so it's easy to send payments to people in your contact list. But also, if you receive a payment from someone in your contact list, then you can kind of indirectly infer their name, and if you have a photo for them in your contact list, you can also pull up a photo. And all of this is secured by kind of Celo's decentralized phone verification protocol, which during onboarding randomly kind of pairs you with other participants on the network who send you text messages, and you receive multiple of those, in effect, proving with high probability that you have access to a phone number. And really excited, as of this last release of Valora, C Labs now pays for your phone verification costs using meta transactions. And so It's free to get started, really easy to get onboarded. So again, highly recommend checking that out. And then kind of probably most interesting with respect to kind of today's talk, Celo really from the ground up has been built with kind of this mobile first mindset. We'll talk about the consensus protocol in a bit and how it's very efficient, but also there are other things like full node incentives that incentivize people to run full nodes to service like clients running on the network. And so I'm sure for this audience, this graph needs no explanation. These chain sizes have been growing obviously a lot. These numbers I pulled yesterday, 302 megabytes for Bitcoin, 574 gigabytes for a full node sync with Geth on Ethereum. Clearly too much data to download on a mobile device to sync. And on the flip side, mobile device adoption continues to grow. Some people kind of get surprised when they see just how big these numbers are. Last year, there were 8 billion mobile devices, not including IoT devices, that had active mobile subscriptions in the world. And this year, we crossed the 6 billion mark for smartphone devices with active mobile subscriptions. Again, that's just a staggering number. And it also really underscores just how big of a percentage of these mobile devices are now smart devices. I think feature phones are really rapidly, globally being completely eradicated. And then if you look at the colors of this chart, you'll see that the connectivity is also actually really impressive. So over 60% of these 6 billion smartphones now have LTE, 4G, or better connectivity. And by 2025, that will be over 80%. Again, really, really big numbers. And so mobile is clearly already here and continues to be kind of the future. And, obviously to Satoshi's credit, she kind of foresaw this and came up with kind of this simple payment verification protocol that many like clients today are based off of. The protocol is simple. You simply download each header in the chain. If you receive multiple chains from the network, then you simply pick the one with the most proof of work done against it. And once you get to the most recent header, then you can use a Merkle proof API to query state and receive proofs around state that you're interested in looking up. And again, so long as the network isn't being attacked and you can trust kind of that longest chain rule, then this works really, really well. But, it's still a lot of data. Again, these are numbers I pulled yesterday, 53 megabytes of headers to get to the latest header on Bitcoin, 5.7 gigabytes for Ethereum. That is a staggeringly big number, and no one's going to wait to download 5.7 gigabytes of data to get their app going, which is why, as I'm sure many people here know, most mobile wallets today simply trust a third party. And so if you want to build something that is fully permissionless and decentralized, you can't really do it. And then it turns out that this also creates problems for cross-chain bridges. One way of building a bridge is to verify the like client protocol in a smart contract on the network. And that becomes pretty expensive as well. Not in all cases, but in many cases, as we saw with BTC Relay, which ran for a while on Ethereum, bringing Bitcoin headers onto ETH, which died around 2 years ago. And if you're interested in cross-chain bridges, my colleague James Prestwich will be talking tomorrow at, I believe, the same time. So definitely check out that talk as well. So what's being done? You might be wondering what's already been done in the space. And there has been some related work. In the proof of work space, NIPAPAO and Fly Client. used interesting techniques to effectively reduce the number of headers that you have to download to a number that is logarithmic in the length of the chain. I think for Ethereum, this roughly ends up being around 500 kilobytes of data, which is definitely a lot better than many gigabytes. Unfortunately, these techniques don't really work in proof-of-stake settings, and so we weren't able to leverage them. On the proof-of-stake side, you probably have also heard of Coda, which is using kind of interesting recursive SNARK composition to effectively prove that a block and therefore a header is part of the chain. And this is very interesting. Unfortunately, there's a few trade-offs. Probably most importantly for us, it limits what you can do in the smart contract setting. It's, as I mentioned, Celo is fully EVM compatible, and so if you want to maintain that compatibility, it would be quite difficult to be able to construct proofs that verify the correctness of an entire block and the entire execution of that block. And so in this work, we focused mostly on the light client, which again, for a use case of those kind of social mobile wallets is actually sufficient. And so how does Plumo work? It works in the context of Celo's proof-of-stake protocol, which is similar in many ways to Cosmos. We use stake to kind of elect hundreds of validators who then perform PBFT-based consensus to kind of agree on valid state transitions in the chain. Validators effectively agree on such a state transition by signing kind of the headers or the header of each block that they validate. And so long as 2/3 of these validators sign off on a particular header, then it's deemed kind of validated and final. And so in this context, if you wanted to build a simple light client protocol, you can do so by effectively modifying the SPV algorithm that we just talked about. You download all of the headers since the beginning of the network. You can then use that to construct or to validate, I should say, Merkle proofs that full nodes send you. And then rather than just checking the proof of work along the way, you instead just check that 2/3 of validators signed off on each header. And then if the validator set changes, then you just need to keep track of those changes. In Celo, the result of the any validator election is encoded in a diff in the header in addition to kind of smart contract storage. And so a light client can simply notice that there's changes to the validator set, apply those changes as they're kind of verifying these signatures. And so this works, but again, it would likely have kind of a similar amount of data that you would have to download to kind of what we see already today on something like Ethereum. Because Celo has even shorter block periods than Ethereum, 5-second block times, this would quickly become prohibitive for any mobile device. And so to improve on this, it uses kind of 3, I would say, new innovations. Number one, it uses kind of the concept of epochs, where the validator election can only happen in an epoch header or the last header in that epoch. And so for the current mainnet, epochs last about a day. And so an election can only happen once per day. And so this means that within that day, a light client can verify a header in any order that it so chooses. It doesn't have to download all of them. It knows the validator set will stay the same, so it can verify that 2/3 of those validators have signed off on that header in any order that it fetches them. And it also means that if it's syncing from the beginning of the network, it only has to download the last header of each day instead of every header, because that's the only time that the validator set can change. And so if you take a 1-day epoch length, and if you have 5-second block periods, then this ends up being a 17,000 times reduction in the amount of data that a light client has to download. So that's pretty significant already. Next, like some other recent networks that have launched this year, Celo uses BLS signature aggregation to aggregate the signatures that each of these validators are leaving on each header into a single constant size multi-sig and a bit vector of all of the validators that have signed. If you factor in the and this is by contrast to kind of some earlier proof of stake networks that just simply have an array of all of the signatures from all of the validators. And then if you factor in the rest of the header size, this results in roughly a 10x reduction in the amount of data per header. And so these two optimizations are what the network launched with. And given that the network has been around for on the order of 6 months, it's still very quick to sync. And if you spin up Valora today, it syncs with the network near instantly. But as the chain grows, that will change. And so what we're rolling out very soon is the use of SNARKs to effectively prove this existing light client protocol that I just described into a non-interactive constant size 500 byte size proof that mobile phones can verify in constant time to effectively make this much more efficient over time. And so what do these SNARK proofs have to do? For each epoch, they effectively have to perform kind of the light client protocol. This means that based on the current bitmap, you have to see which validators signed. Again, only 2/3 of validators need to actually sign. So if maybe one is offline and 99 sign, you would have to verify the signature of those 99. The way to do that with BLS aggregated signatures is you actually have to aggregate the public keys of each of those 99 validators according to this bitmap. That gives you the aggregated kind of public key. Of course, you also have to check the bitmap to see that 2/3 of validators did in fact sign. And then, of course, you have to check that the epoch number has in fact grown by 1. Then you encode this epoch into bits and hash to group, and then you can compute and actually check the overall BLS signature. And so we do all of this in the SNARK circuit, and that works for one epoch. But how do you prove this across multiple epochs? Ultimately, that's how we get this extra benefit from these SNARK proofs. We could do it in one of two ways. We could either recursively compose these proofs by proving the verification code that verifies the previous proof, in addition to doing what I just described on the previous slide. This works quite nicely. You end up getting a single proof that, or this could work quite nicely in that you would get a single proof that you could then verify, and you would know that the header associated with that proof was in fact in the chain. Unfortunately, verifying or proving the verification code is obviously quite complicated and requires either fairly new cryptography that hasn't been used in production environments before, or really big elliptic curves or cycles of elliptic curves that just would be prohibitively expensive to actually deploy in practice. And so rather than that, Celo uses a slightly different technique using the more conservative Grot16 proving system which has been around for a while, has been used in Zcash, most obviously, but as well in many other places. And instead of recursion, we use induction, and we effectively just prove a large number of these epoch headers in a single proof, almost sequentially, such that that proof then allows clients to simply fast forward and kind of jump from kind of this one header on the left to the header on the right once they reach the header on the left. And so long as you can have proofs that allow you to jump a good amount of distance, then this really can be quite effective at decreasing sync times. The overall complexity is still linear, but your constants become much smaller. And so this is in fact what Plumo does. Because checking BLS aggregated signatures requires pairing operations, and because those are typically prohibitive in SNARK circuits, we employ a technique from Zexi, which uses kind of one level of recursion. We actually construct all of these proofs in the BW6 curve, which then allows us to efficiently construct proofs of pairing operations over the BLS 12377 curve that we use for actual signing of these headers. So that's kind of the summary. What does this end up performing like? When it comes to the proving times, they look roughly like the following. So where the proving times grow with the number of epochs and the number of validators. And so this number is for 150 validators and 135 epochs, which is just over a third of a year. And on Google's biggest machine that you can rent from Google Cloud, one that has 160 CPUs and 4 terabytes of RAM. This takes on the order of an hour and a half to construct one of these proofs. That is a big machine and a lot of RAM. And an hour and a half, it takes, is a significant amount of time. But it turns out that these machines, especially if you buy a spot instance of these machines, it only costs $6 an hour. So we're talking about $9 to construct one of these proofs. We only have to construct one of these proofs once per day. And as soon as really anybody on the network constructs one and gossips it out, then everyone can verify it, and it can be spread amongst the network. And it will instantly allow clients to start syncing more quickly. And so the public benefit of that $9 a day is just enormous. And so it's easily amortized. And there are teams that are looking to do this in FPGAs. We also have some working graphics card code. So there are ways to even decrease this cost more, although really $9 is pretty impressive as is. On the verification side, it takes a constant amount of time to verify one of these proofs, regardless of how many validators or epochs are in them. And the numbers look like the following. On really the oldest device that we could find, I think it's 6 or 8 years old, I forget, one of these Moto G2s. It does take around 6 seconds, but on a more recent device, we're talking about on the order of 1/5 of a second to verify one of these. Very, very reasonable and significantly faster than having to download a third of a year's worth of epoch headers. And then verify them, which also does take some time. Now, these verification results are slightly out of date now. These are from work that we did before on the SW6 curve, and we've actually migrated now to BW6, which is a much more efficient curve. And so these numbers are expected to be around 3 to 5 times faster. And the team worked really hard, but we weren't able to get these new numbers in time for this talk. But do stay tuned. These numbers will look a lot better soon. So some of you might be wondering what's new. Maybe you've heard about Plumo before. There's a bunch of really exciting things that I wanted to share as part of this update. Probably most critically, we are now code complete for all of this SNARK-based logic. It will be launching in the next Celo hard fork, dubbed Dona, which will happen in Q1 of next year. Really exciting. A lot of the code is now out for audit, and there's teams that are combing through the SNARK logic and the syncing code. So that's really exciting. With this launch, we're going to be adding new slashing conditions, of course, so that a validator can equivocate between the kind of SNARK and the non-SNARK data, and also for creating forks on the SNARK data. So that's exciting. And then perhaps most impressive, there's been a fair amount of work that has gone into optimizing the performance of this, both using some really interesting arithmetic optimizations, but also some hand-tuned assembly for x86 and now also for the Apple M1 chip as well, which is awesome. And then there's also, as I mentioned before, beta graphics card support. And it turns out that this work, if you look at the performance, wasn't really required for running the network for constructing those proofs. This work yielded kind of a 2 to 4x improvement in kind of proving time, but it didn't really matter even if proving took longer. We have ultimately 24 hours to construct those proofs, and those machines are still relatively cheap per hour given the public benefit of these proofs. But it turns out that these optimizations were needed because in addition to the proving time, the amount of time needed to contribute to a trusted setup ceremony for the SNARK systems also was quite big. In fact, before we did the work, it was on the order of 3 to 4 days that everybody would have to run their kind of fairly beefy CPU, fairly beefy desktop machines in order to contribute to the ceremony. And if you wanted 50 to 100 participants, 3 to 4 days times that, we were talking about very, very long periods of time needed to perform the ceremony. So we did two things. We did these optimizations. So now it's on the order of 12 hours to 24 hours to participate in the ceremony. And we took some ideas from Justin Vitalik to effectively parallelize kind of a Powers of Tau ceremony so that all of this computation can happen roughly at the same time, which then again really dramatically lowers the amount of time needed to do the setup. And so that setup, we just announced it. It's coming soon. So it's really, really exciting. I think by just the raw amount of computation that will be needed to perform the setup, this will probably be the biggest one done to date, and certainly the first one to be done in parallel, which is really exciting. It's going to be big because the circuits are big and because the BW6 curve is big. And so if you're interested in hearing more, definitely go to tinyurl.com/plumo-ceremony. There's a blog post there that outlines the whole thing. It's very interesting. And then if you like participating in these things, and I highly recommend it, these setups are effectively can be trusted so long as only a single participant acted non-maliciously. You can be that participant, and so highly recommend signing up. They're really fun to do. And if you're interested, definitely check out tinyurl.com/Plumo-signup. Yeah, and so that's everything. I wanted to thank you all for being here. And if you want to stay connected, definitely check out the following links and my Twitter handle, which to save you guys from having to remember how to spell my last name, I recently changed it and replaced my last name with _. So much, much easier for you all. Awesome.
Thank you so much, Marek. 6 billion smartphones is a staggering number. And the work that you and your team are doing sounds quite fascinating, but very much so quite challenging. So thank you so much for the time today.
Absolutely.
We have a couple questions in the Q&A. First question, what technical developments are you most proud of?
Yeah, that's a really great question. So the Celo platform has so many different innovations that it's really hard to even spend 30 minutes going through them all. And so for this talk, I focused on the Plumo part. I think from a technical perspective, the Plumo part is definitely the most challenging. These are massive proofs, never been done types of proofs over really interesting kind of new curves, the BW6 curve. So definitely that's up there. The identity protocol, a lot went into making it practically impossible or effectively impossible to brute force the phone numbers and to infer who's using the platform. To do that in a decentralized way was very, very difficult and very interesting. And the end result is that you get a really beautiful user experience where you can send payments to people in your contact list. And so I would have to say that, yeah, maybe that just ekes out and is more proud of that over this.
Awesome. Another question here. What are the biggest challenges with a mobile-first blockchain platform?
Yeah, consensus for sure, right? This is the biggest thing, right? This is why most mobile wallets don't really try to do decentralized consensus or verify decentralized consensus on mobile devices. And so this was, I would say, the biggest challenge.
Awesome. Thank you so much for your time, Marek. I'm very excited for the future of Celo. Thank you for your time.
Absolutely. It's great being here.
Thanks.
Have a good day.
Take care.